as I had left in the last slide about the transitions from level E1 and E2, and what I plan to do is, see, I just brought this picture in because just to recollect. So, we have a transition from E1 to E0. Okay. It need not be a lasing transition, it need not be a laser, it can be a spontaneous light that is coming through. So, this particle from here, atom or molecule or whatever, it is tumbling down to level E0 and it is giving out a, say, a spontaneous emission. Okay. And now you would expect that the light from this spontaneous emission would be a single line or a single frequency. And what I want to tell you now is that's not true. It's not exactly monochromatic. Okay. So, the radiation that is coming out from here, okay, you could depict it as a sinusoidal wave like this. Okay. It is a nice sinusoidal wave. This is a t axis and this is the amplitude of the sine wave. So, this is the electric field of the radiation. Okay. Now, what I want to know is what is the frequency of this. Okay. So, when you see visually here, you can see there is just one frequency, whatever be its frequency. If I were to draw this in the frequency space, I would have frequency in the x axis nu, and this is the intensity of that frequency or wavelength, whatever you might want to call it, which is f nu. The frequency here in this sinusoidal wave is nu 0, it is one single line. Okay, it is shown as a fat line here, but it is just one single line. So, there is just one frequency. Now, what can happen is, as the radiation is being emitted here, spontaneous or lasing action, anything, it will undergo certain changes as it comes through. That means the amplitude of this radiation will become lesser and lesser. So, I will depict it in this. So, it remains as a sinusoidal wave, okay, like this, but then the amplitude is slowly decreasing. Okay. This is what happens to any light. Okay. Any light or any wave, it can undergo changes in its amplitude. But if you notice here, there is a slow frequency here. That means the amplitude is reducing at a certain slow frequency. And if you were to extrapolate it, it can just go like this, it can become a wave by itself. Okay. So, then you have the inherent frequency, which is this, and on top of that is superimposed another frequency, which is this slow fall. Again, if you notice here, if you see visually, the frequency here has changed a little bit from this point. So, even that might happen, the frequency itself might undergo certain changes. So, not only that the amplitude is going down, but okay, frequency. That means intuitively itself you find that just visually you can find 3 frequencies. Okay. And but there may be much more. So, it does not remain monochromatic anymore. You know, along this central frequency of nu 0 here, you have other small frequencies which are happening. Okay. That means you have a kind of a broadening of this line. The line is no longer a single line like this. There is a broadening, and this is called the line shape function. Okay. What is the shape of this line? That is because those additional frequencies have come into being, and on either side of nu 0 you have so many frequencies, so you get a broadening. But mathematically you would like to quantify this broadening. Okay. How much has it broadened? And the way to quantify it is the full width at half maximum. delta nu. Delta nu is called full width at half maximum, and in short it is called FWHM, and that is this width here shown by this red arrow. Okay. Full width because it is from this side, from the left hand side of nu 0 to the right hand side of nu 0, and half maximum because it is measured at half of the peak value. So, what is the peak value of f nu? You find out that, you take half of that, you come here, and at that half value of the peak you find out what is your frequency nu, and this becomes the full width. Okay. So, it is a very important broadening parameter which is given in many places. So, this is what you have understood a little bit about the line shape and the broadening, and these are the terms that are used. Okay. Now, I will give you a slightly more detailed version of the frequency space, and how do we transform from the frequency space into the time space and back again to the frequency space. Okay. That is done by mathematically by something called the Fourier transform. Okay. So, let us see what exactly is a Fourier transform. It is a mathematical tool which really helps you travel from the time space into the frequency space. So, just have intuitively just these diagrams have been given just for intuitive picturization. So, here again is a sinusoidal kind of wave. So, for that you have a single frequency here. So, this is the time space here, all the diagrams here are in the time space, and all the diagrams here are in the frequency space. So, here you have a single frequency, but suppose it is slowly falling down like that, you can see the slow frequency also. So, I add one more frequency. So, you might get two lines in the frequency space. Now, you go to the next picture, that is this. So, here you have again a sinusoidal kind of wave, but it is modulated by this red line which you can see, which is a slow frequency as compared to this. Okay. So, I have this, the blue frequency will be shown here, and the one corresponding to the red frequency line is here. Okay. So, here again you can see there are two frequencies, nothing more than two. Now, just come down to the next picture. In this next picture, focus on the yellow line. Okay. Now, this yellow line, it is not easy to write down mathematically. Okay. This yellow line, it has got some kinks and peaks and kinks, and here it goes and what. But actually this yellow line is a combination or addition of a few other sine waves or cosine waves. So, you can see this green line, that is a sine wave, you can depict it even as a cosine wave, or you can see this line, the red, this red line, the smaller one, or it may be purplish line, which is again a very regular frequency, very regular wave with a certain frequency. Then you have this green line, okay, again that has a certain frequency and it is very regular. So, the yellow line is really an addition of all these frequencies, 1, 2, 3, 4 and 5, 4 frequencies, yeah. Yes, 1, 2, 3 and this fourth one, 4 frequencies. And so, there are 4 frequencies. So, you can very well represent it on a frequency domain as these 4 lines. Okay. But what will happen if you have a picture like this? If you have an electric field which varies like this, you know, nothing specific, you can't really define it, you know, in any particular way. In frequency space, it will look something like this. This is nu and this is f nu. So, it will have some kind of a line shape function, as I had said before. This is the line shape function. That is because within this line shape, you have so many numerous frequencies which make up this wave. Okay. So, what does Fourier transform do? So, for that you must know what is a Fourier series. Okay. So, in a Fourier series you can write the function ft as a summation of cosines and sines. Okay. So, you have ft a0 plus sum of a cosine function, another sine function, and then there are some constant a n, b n. Now, to make it a little more compact, since sines and cosines can be written in terms of complex exponentials, the Fourier series can also be in the complex form. Okay. So, here you have a complex form ft, you write it in terms of Cn e to the power I omega t. Okay. A0, An, Bn, Cn are all Fourier coefficients. To analyze the frequency content of any signal ft, we can use the Fourier transform. So, here we have defined the signal in terms of the sine and cosine waves and also in this exponential form. Now, we use the Fourier transform between the function representation in time domain and the representation in the frequency domain. So, in the frequency domain f omega is integral over ft, that means this ft e to the power minus I omega t dt. Okay. This is called a Fourier transform. So, you have transformed from ft into f omega. Here if you see, you have got omega. So, here you have just integrated out the time and you have left the omega part. So, that is the frequency space. I have introduced purposefully the factor omega because quite often omega and nu are used in literature, in papers and everywhere. So, omega is generally the angular frequency and it is related to nu as omega is equal to 2 pi nu. Okay. Both are frequency, one is angular frequency and the other one you just call it as a frequency. Now, the inverse Fourier transform is given as ft is integral over f omega, capital F omega e to the power I omega t d omega. Here you are integrating out all the omegas, and what you are left with is only the time t. So, that gives you the function ft. So, this is the Fourier transform and this is the inverse Fourier transform. That means you can transform between the time space and the frequency space very easily. Okay. So, it is a kind of a mathematical way of representing and quantifying for that matter. Okay. Let us see now. Okay, here I have spoken about the frequency space here. So, you have a line shape function and you have a broadening. Now, we should know what are the different kinds of broadening that are possible. What are the different kinds of line shape functions that are possible. So, the first one to talk about is the natural broadening. It just natural broadening, I mean from the name itself it is apparent. It just happens because a molecule or an atom is falling down to a lower state and it is giving out a frequency line and that naturally is broadened. And so, we will just go through a bit of the derivation here to know why it broadens naturally. Why does not it remain as a just a single delta function line. Okay. So, here it is. So, if you recall that the number density of the atoms, molecules, particles that decrease in level 1 due to spontaneous emission from level 1 to level 0. Okay. Just try to recall the previous slides and you will know that. And try to recall this equation also, dn1 by dt is equal to minus a10 n1. If you remember, a01 was one of those Einstein's coefficients and n1 was the population density obviously of the level 1 and it is falling down to level 0. Okay. So, obviously, it will depend on n1 here. And a10 had a unit of rate. So, it gives you the rate at which the molecules fall down from the higher level to the lower level. Okay. So, as the molecules fall down, it is emitting all this spontaneous emission. So, obviously, we can equate this or equate this to the intensity of the spontaneous emission. Okay. If this is large, if the number of molecules that are falling down from the top level to the bottom level is large, then obviously the intensity also will be large. So, di by dt, writing an equation exactly similar to this, is equal to minus A10, that is the rate at which the radiation is emitted, and again the intensity. So, we have replaced N1 by I which gives the intensity. So, for every transition a photon is released. The electromagnetic energy emitted per unit time per unit volume, that is I, which is somewhat the intensity, will be following a similar equation as that of N1. So, that is why I have written this. Now, you just focus on this this differential equation. You bring the I onto this side. So, you can write it as di by dt minus A10 dt, and if you take the integral on both sides, you are taking the integral here, you work out the integral, and I turns out to be e to the power minus A10 t. Okay. So, this is the intensity of the electromagnetic energy that is being emitted. Okay. Now, now I is equal to E square. Okay. E is the electric field, I is the intensity, I is equal to E square. Intensity is square root of the electric field. Okay. So, what would be intensity is square of the electric field. So, in order to know the electric field, you have to take the root of I. So, E of t is proportional to, if you take the root of this. When you take a root of the exponential, you just get a 2 below here. Okay. And if you recollect in the previous slide, tau sp, that is tau spontaneous, okay, T spontaneous is equal to 1 upon A10. Okay. It is understandable because A gives you a rate. So, 1 upon A will always be something related to time. Okay. So, that is T spontaneous, that is the time the particle remains on the higher level before it tumbles down. Okay. So, T spontaneous is the spontaneous time of emission or the time it remains on that state. Okay. Quite often if the particle remains for a very long time in the upper state, we call it metastable state. Okay. And okay, so here it is. So, so the electric field becomes proportional to e to the power minus t upon 2 spontaneous. So, I have just replaced A10 with t spontaneous, relating it to the time it remains in that higher level state. But then the electric field of the radiation is also a sinusoidal wave. Okay. That is what we have seen in the previous sign. Any radiation, it is a sinusoidal wave. So, a sinusoidal wave in the time space can be written as E t is proportional to e to the power I omega 0 t. As we have seen in the previous slide, omega 0 happens to be the central frequency. Okay. And so E t now can be written as the sinusoidal wave, I have it here, plus at the same time E t is also e to the power minus t upon 2 tau spontaneous. Okay. So, E t is proportional to this and this. So, you multiply these two. So, you can see that this works out to be something like an amplitude. E0 I have just put a constant there, you can always normalize it. So, finally, the electromagnetic field in time space is given by this formula. Okay. And this part is the sinusoidal part, and this part is your amplitude. So, you can see this amplitude is reducing, e to the power minus 2 is reducing. Basically, this represents, this previous represents this. I have just written this you know, a sinusoidal wave which is falling down, the amplitude is reducing at this rate, something of this kind. So, this gives a broadening, okay, and that is called the natural broadening. Okay. Here I have, in order to calculate the spectrum of the wave, we have to find its Fourier transform. Okay. So, f omega is dt integral of e to the power t e to the power minus I omega t. So, this is the formula of the Fourier transform. So, what do I have to put in here? F omega is here, and all I have to do is put in the value of E t, which I take from this green equation, okay, this green equation here. So, I just put it in here, okay. And you do a little bit of algebraic jugglery and you will come to this. Carefully do those algebraic jugglery and then take the integral, okay. Take the integral from 0 to infinity, where t, I have taken it from 0 to infinity because I have to integrate over time t, and t is 0 at the time at which the atom starts emitting the radiation. And the spectrum associated with the radiation. So, when I take the Fourier transform, it comes out to be this. You have to do it very, very carefully, slowly, and it is very easy. You can do it and you can come to this conclusion. Okay. In the frequency space, f omega is given by this. So, I have a tau spontaneous. So, my f omega is dependent on how long the atom, molecule or that particle stays in the upper level. Okay. So, it depends on tau spontaneous, and of course, the central frequency is omega 0. Okay. So, this is what, but again this is a imaginary function, I comes in, we have to somehow get rid of the I. So, now the trick that is used is this radiation is f, this radiation that is coming out, the spectrum is associated with this f omega mod square. So, the line shape function is given by g omega. Okay. So, I will take basically the mod square of this function, okay, because that will give me the intensity of the intensity in the spectrum, and at the same time it's I will get a real value, I will get rid of I. Okay. So, what does it look like? You do all that, g omega is the final line shape function, g omega is given by this huge big formula here, okay, this big formula, and you can see it looks like a Lorentzian function. On this green side, on this side I have just put in the actual Lorentzian function, what a Lorentzian function looks like. Okay. So, if you compare these two, you will see that g omega is also a Lorentzian function, and the line shape looks something like that, which follows this red line, and the width, full width half maximum is here between these two blue arrows. Okay. This is the line shape function, and that is between the blue arrows is the full width half maximum of this line shape function. Now, just compare these two. If you see here tau is actually the full width half maximum of any Lorentzian function. So, if you compare this with this, so tau is equivalent to 1 upon T sp. So, delta omega is 1 upon T sp. Tau is the full width half maximum, tau is equivalent to 1 upon tau sp. So, the full width half maximum is delta omega is equal to 1 upon tau sp. Okay. Here I have just put in a set of formulas, so that just gives you a reminder of how to calculate delta omega and delta lambda. Quite often the full width half maximum may be given in terms of delta lambda, and so you just have to know the conversion of omega to nu and to lambda. So, here it is, omega is nu is equal to omega by 2 pi, and delta nu is equal to 1 upon 2 pi tau sp, and nu is given by c is the velocity of light upon lambda, and delta nu is C upon lambda square. Delta lambda is this. You see, when you take this delta lambda, you have to be very careful. Delta nu, you have to take this differential, okay. Nu and C by delta lambda. So, delta lambda, if you take the differential, is becomes C upon delta square delta lambda. So, this is a whole set of formulas that you just keep at the back of your mind, okay. And you start calculating the line shape functions of, say, a sodium line, or say the line shape function of the cesium line, or say the line shape function of the helium line. So, all these in the blue structure, if you see, I have just given it for comparison, and the units that are generally used to define the line shape functions and to define the full width half maximum, and it is a good comparison. See, for example, for the sodium line, which is the D line, or the 3p to 3s transitions, that lambda is equal to 589 nanometer, tau sp is equal to 16 nanoseconds. That means the particle remains before it emits the D line, it remains in the upper level for 16 nanoseconds, okay, nanoseconds, 10 to the power minus 9 seconds. And delta nu in this case works out to be 9.95 megahertz. So, megahertz is a unit in which you give delta nu. That is the full width half maximum. But if you are giving full width half maximum in terms of delta lambda, okay, if you are giving it in terms of that, it works out to be 0.0115 picometer. Pico is 10 to the power minus 12 meter. Okay. So, these are the units, you just get a comparison. Then if you compare it with cesium, you will find the cesium line is broader than the sodium line. Okay. If you compare it with helium, you will see the helium line delta lambda is very small, okay, as good as 0, but okay, it does have a width in picometer. So, out of the 3, if you see, the helium line is the smallest. Okay. Just concentrate on these blue squares and try to compare and see in your mind. You just get an idea of the units used and keep it at the back of your mind. So, whenever you are comparing, it is better to keep the units in your mind. Okay.